from various parts of our country. Very good morning to all of you. So it is a great privilege and honor to address all the teachers on this occasion of the part of the Space Educators Training and Knowledge Upgradation Program. Really, it is a unique opportunity to be with you. In fact, I would have been happy to meet most of you, but then it is arranged in the online mode. Now, dear friends, you are all playing a very, very crucial role. I understand the teachers from 9th standard to 12th standard are participating from various parts of this country. Now, when you look at our country, we got independence in 1947. And from that 1947, last 76 years, we have grown to greater levels in multiple fields. In fact, you all may be knowing, almost 97% people were below poverty when we got independence. And from that stature, today, the country is in a position to produce food grains and export to other countries. And every field, you take agriculture, rural development, IT, transport, power sector, and education sector, health management, and infrastructure, every area the country has developed. If you take a strong foundation for any country is the education. When we look at 1947, almost 12% people were only, the literacy level was hardly 12% level. From that, now the number has come to close to 80%. And at that point of time, 1947, we had hardly 2,825 schools in the country, which has grown to almost 8.4 lakhs. And there was no IITs and great academic institutions. And today, the country has established a great and strong education system like IITs, IIScs, IIMs, and All India Institute of Medical Science, ISRO, and whatnot. Now, if you look at currently, we are having something around 4,351 engineering colleges in the country, 742 medical colleges, and India is the enrollment of students in the college is something around 30.6 million. And that shows the growth in the education sector. A country which has to grow to greater levels, solely the education plays a very, very crucial role. And it is in that area that the school teachers, really you provide strong foundation for the next generation of this country, and you are contributing. First of all, my greetings to all teachers who are really participating in this program. In fact, teaching is one of the noble profession through which you contribute for making this country as a developed country. When we celebrate 100 years of independence only, I can say confidently the way the growth has happened. We have become the fifth economic power, economically fifth status, and we are aiming to become third status before 2030. And surely India is having high growth rate in every field, and you people are the great contributors. So with that introduction, let me go to my talk on the launch vehicles and propulsion system. That is the topic on which I am going to address to you. So one area we have grown is the space sector. 1947, when we got the independence, there was no space program in the country. And in fact, the space program itself started 1962 only. And we are a 60 years plus old organization. And today, really the space program is really doing great service for the country in multiple sectors. So today my talk will be on launch vehicles and propulsion systems. Now, almost after 15 years, we got independence. The visionary leader, Dr. Vikram Sarabhai, he was really strongly having the vision, and he felt at that point of time, and the advanced space technology can be used for the society and common man of this country. And to do the service of the space system for the common man, what we need is satellites of different types, and that has to be conceived, built, and we have to place in the orbit. To place it in the orbit, we need our own launch vehicles. And of course, we need ground segments for sending the spacecraft and ensuring its utility. So these three areas, in fact, the development started concurrently, and today really the space is doing great thing. And you all know, last year, August 23rd, 2023 is a historical day for Indian space program. India is the first country and only one country successfully landed close to the south pole of moon and made all Indians proud. Now, if you look at the organization per se, 1962, the space program was per se initiated in a village called Tumba, a fishing village near Thiruvananthapuram. And you can see the church building. This is the church building. This entire activity was started at that point of time. Now, coming to the growth of the organization, it was on 21st November 1963. We had the first rocket launch from Tumba, and that rocket was not our rocket. It was a rocket from other country, rather USA, and the payload came from France, and a lot of equipments came from other countries, and we assembled and we launched. So that was on 21st November 1963. And from that, we moved to our indigenous rocket development program on 20th November 1967. Easy to remember this date. First launch was 21st November 63, and this was 20th November 1967. We had a tiny rocket, our indigenous rocket called RH-75 rocket, which is 7 kg weight, and which it took off from Tumpa soil and went up to a altitude of almost 9.3 kilometers. Now, as teachers, I want to present to you one slide. You look at when we started our program 1967, when we had the first launch of RH-75. I have given in the middle our rocket, and at that point of time, other countries, if you see, it was in 1957 that the first rocket, the satellite, the Sputnik, was launched in 1957, and then 1961, the Yuri Gagarin. That was the first manned mission accomplished in the world, and it was done by USSR. And 1969, I was studying the first standard, sitting in a classroom, not on bench or table, on a bench or chairs, on the floor. I was sitting in a village school, studying in the mother tongue. I was in the first standard that day, July 16th. It was a very happy day for us, because we as students, we were not knowing what is happening, but there was teachers who were not teaching. They were going here and there with trying to get the message. And finally, the teachers were telling man has, the confirmation has come that man has landed on moon. So that is the place the world was standing, and we started the program with a tiny rocket of 7 kg. From that humble beginning, today we have come as a successful organization, and almost so many types of sounding rockets we have realized. And from India, both Indian and abroad foreign sounding rockets, something around close to 4,000 sounding rockets are sent for studying the atmosphere. Now, another important major milestone was accomplished on 18th July 1980, the first satellite launch vehicle, the SLV-3. That was the second vehicle and first successful vehicle which placed 40 kg satellite in the low Earth orbit. And India joined the elite group of spacefaring nations having that capability at that point of time. And the project director was none other than our people's president, APJ Abdul Kalam, under the guidance of our the then chairman, a great person, Professor Satish Dhawan. This mission was accomplished. From that beginning of placing a 40 kg satellite, and launch vehicle mass was something around 17 ton was the mass. Today we have grown to greater and greater heights. There are 6 generations of launch vehicles we have developed. I think you can see the numbers. The first is the SLV-3, and the liftoff mass is something around 17 tons. And the vehicle is the ASLV, which is having capability almost the 3 times capability of the SLV-3. Almost it can place 140 to 150 kg satellite in the low Earth orbit. Then we moved to the operational programs. In fact, SLV-3, ASLV, we were learning a lot of launch vehicle related technologies. And then today, and the GSLV, Geosynchronous Satellite Launch Vehicle, GSLV Mark II, and launch vehicle M3. Now, if you see the capability, I think all the numbers are there, you can understand. The PSLV can place something around 1100 kg payload in the geo transfer orbit, or something around up to 1700 kg in the low Earth orbit. And when it comes to Mark II vehicle, it is almost 2 times of the PSLV capability. It can place up to 2200 kg in the geo transfer orbit. Geo transfer orbit is something around from the Earth. One side is something around 170 kilometers, other side is its elliptical orbit, something around 36,000 kilometers. That is the orbit. It can place the GSLV capabilities 2 times of the PSLV. Then comes to the Mark III. Mark III was launched almost 37 years after the SLV-3 launch. SLV-3 successfully launched in 1980, and this was done in 2017. And the launcher mass is in 37 years, from 17 ton, it was 37.4 times higher than the SLV-3 mass. Something around 640 to 642 ton is the liftoff mass, and capable of placing something around 4,200 kg in the geotransfer orbit, or around 9,000 kg in the low Earth orbit. That is the capability of the vehicle. And coming to a new vehicle we have developed called small satellite launch vehicle, that is capable of placing 500 kg satellite in the low Earth orbit of 500 kilometer orbit, and it is having mostly all solid propulsion. So anytime we can build the satellite within a week time. Once the customer wants the satellite to be placed, we will be in a position to build the satellite and launch. So this is the fleet of launch vehicles what we have developed over the years. Now coming to the overall accomplishments, already you would have heard from other colleagues also. Lot of accomplishments, and as I told, close to 3,900 Rohini sounding rockets and something around 94 launch vehicle missions. And 1975 we launched the first satellite, Aryabhatta. From that, today we have gone a big way. Almost 124 satellites are launched, and 432 satellites of other countries we have placed in orbit. And there are so many experimental missions. And the satellite from 40 kg SLV-3, we have built the GSAT-11, which is 6,000 kg satellite. That is the type of capability which has come in the satellite area. Same way, in the payload development, which is done by our Space Application Center and other areas, payload development also, lot of development has taken place. And coming to the launcher, the launch vehicle is meant for placing the satellites in the required orbit. Basically, the launcher has to lift off from the launch pad, taking the satellite and move in the optimally designed path and place the satellite in the required orbit. But then I would like to say a couple of differences. If you take, for example, you take a car, the speed of the car is something around 100 to 120 kilometers per hour. And aircraft velocity is something around 800 to 900 kilometers per hour. Now, if you have to place a satellite in the geotransfer orbit, we have to give a velocity of something around 37,000 kilometers per hour. And low Earth orbit something around 20,000, 25,000, depending upon the orbit. That is the type of velocity which we have to give. And the launcher has to really lift off from the launch pad, and it has to move in the required optimum path and give the required injection velocity and place the satellite in the required orbit. And the launch vehicle, if you say, is a interdisciplinary activity. If you look at a launcher, it has got so many systems, starting from propulsion. Propulsion is nothing but the engine and which gives muscle power for lifting of the launcher. And it has got structures, and one need to have understanding about aerodynamics and thermal related aspect, because when the launcher is lifting off, it really experiences heavy aerodynamic heatings and thermal aspects. And in the launch pad itself, when the engines are firing, lot of plume and plume interaction and all those things are there. Then the equipment bay, which is the brain of the launcher, which has inbuilt the computer system and software system, which really autonomous way control the launcher to place the satellite in the required orbit. The navigation, guidance and control system and mechanisms, and large number of metallic and non-metallic materials, and manufacturing for fabricated manufacturing technologies, another crucial area. Now here I have not put everything, few of the things I have put. Basically I want to communicate it is an amalgamation of all branches of engineering, including mechanical, chemical, computer, electronics, civil, structures, aerospace, metallurgy, and all branches of engineering is involved in design, development and realization of the launcher, and the core physics and mathematics. Without that, nothing. And that is there, and chemistry. So we used to say, the launch vehicle community, we used to say it is an amalgamation of all branches of science and engineering knowledge is required for design, development and launching of the launcher. Now, the couple of slides I have put because it will be very difficult to explain all the systems. Number one, when you talk about a launch vehicle, basically the function is it has to place the satellite in the required orbit. It has to safely lift off from the launch pad, cross through the dense atmosphere, move in the optimum required path, and place the satellite in the orbit. So once we get the input related to what is the type of satellite, where it has to be placed, then the entire configuration study, the vehicle sizing and mission related aspects and aerodynamic related aspect, control studies, everything is done hand in hand simultaneously. Finally, the launch vehicle is configured. Now, one of the system called launch vehicle structure. Actually, if a structural engineer stands in front of the launcher, he will see the entire launch vehicle as a structure only, because it is the full of structures built which has to withstand the extreme operating conditions like temperature, then the extreme environmental loads, vibration, acoustic conditions, everything it has to withstand. And we cannot design the launchers like ground systems, like our bridge or something. Here we have to use very optimally, because a launcher, for example, a 640 ton launcher can place only something around 4,200 kg satellite, useful satellite in the orbit. If the launcher mass is more, then the launcher will not take off from the ground, it will be only in the launch pad. So one has to optimally design the launcher and its structures. And another important thing is the aerodynamics. When the vehicle is lifting off and going through the atmosphere, it is moving with a high velocity, and one has to have a full understanding of the aerodynamics and what type of loads are going to act, what type of thermal environment it is going to really experience, and one has to do extremely detailed analysis, aerodynamic studies through computational fluid dynamics. Also, we have to do wind tunnel studies with small models to understand the type of loads what is going to experience to finalize the design and realization of the launch vehicles. Another thing is the thermal environment. Number one, when the launch vehicle is going, it experiences a aerodynamic loads. So the satellite, everything has to be protected. So you need a proper thermal protection system. And again, the whatever fuel and oxidizer we use also has to be kept in the proper conditions. And for that also thermal protection is required. And whenever we talk about some sort of modules coming back to the atmosphere, it has to cross the dense atmosphere and it will experience very high temperature. So thermal system design and realization is another important area. Then launcher is a single made up of multiple subsystems built as a single vehicle, and then to do the proper separations and jettisoning of area system, lot of mechanisms are required. Another thing is pyro systems. Pyros are, like small, it is a high energy material used for initiating the ignition, separation, and even some of the valves which are isolating from the environment to open or close the valves. These pyro systems are employed. Navigation, guidance and control, this is another important subsystems of launcher, and the navigation systems measure the present position, velocity and attitude of the vehicle, and guidance system compute the optimal path to reach the required place with utilization of minimum energy, and control system orient the vehicle and command and control system is reorient the vehicle as commanded by the guidance, so it goes to the required path. You know, the difference between the T-body rocket and launcher is a very simple difference. If you see the T-body rocket, it also takes off and goes, but then when you fire a rocket, it will go wherever it wants. Whereas launcher should go wherever we want and to place the satellite in the required place. So that is the basic difference. And to achieve wherever we want, a lot of systems like navigation, guidance, control systems are required. And now if you take this NGC, navigation, guidance and control system, it has got sensors for sensing the vehicle acceleration, vehicle rates and vehicle orientation. Then navigation system compute the vehicle present attitude, position, velocity with respect to the reference frame, and guidance system compute the desired attitude to achieve the end conditions. And autopilot, which is part of the NGC system, compute the control commands to steer the vehicle instantaneously to achieve the required attitude. And there are hardware like control power plants which are there, which changes the direction and orientation of the vehicle to steer it in the required path to achieve the target. Another thing is, you know, it has got both electrical system and mechanical system, and it is all realized as subsystem. The rocket is realized as subsystem. Finally, everything has to be integrated both electrically and mechanically. Actually, 1,000 kilometers of wires are inside a rocket to interlink all the systems. Plus, the mechanically also, when it is subsystems are realized, one has to integrate. This is another important domain. Then telemetry, tracking and telecommand is another important system. Telemetry system is basically when the launcher goes, it has got, we have put a lot of sensors to understand the health of various systems, a lot of measurements like temperature measurement, pressure measurement, then the current measurement and whatnot. So much measurements are there, and the telemetry system is the one which process and transmit the entire parameters. And tracking is another one. We have to, when the rocket or launch vehicle takes off and goes, and we have to really track the entire thing. And this involves radar and communication system in the ground and transponder systems on board to track the vehicle. And telecommand is another important system through which we have to set important commands. In fact, 95% of the commands are on board. But there are a couple of commands which are sent even if the launcher doesn't go in the required path. If it is unsafe, then probably we have to also destroy the vehicle if required. So there is a telecommand system. This is another important system. And once you build the launcher, which has got both the structures, propulsion systems, then the control systems, everything. And once you integrate everything, and one has to, and it is having an onboard computer, which really has all the, it is like a brain of the launcher, and it has got both hardware and software. And we carry out extensive simulation studies a priori to validate the equipment bay, which has a computer and software to understand whether the entire coding is correct, all the systems are working in an integrated and cohesive way, and injecting, simulating extensive operating conditions, the vehicle loads, aerodynamic conditions, then the dispersion on various parameters, and extensive simulation studies has to be carried out. This is a combined work of aerospace team, mechanical team, electronics team, computer science team. It's a amalgamation of all the teams involved in mission simulation and studies. Another thing is, you know, one is design and configuring the vehicle. Then we need large number of materials, both metallic materials and non-metallic materials for building the launcher. And in fact, 100 types of materials are employed in realizing the launcher. And we have also indigenously developed some important strategic materials. Yeah, sorry. Composite materials. Composite materials are high strength and low density materials huge quantity of composite materials we use in the launch vehicle area. And another thing is, once you build a subsystem, we don't go straight away for launching. We have to really test each subsystems. For example, take a structure. We have to, after realization, some of the hardware, we have to exclusively test and qualify, simulating all the type of loads, whatever is going to be experienced by the launcher. So we have to put through the different types of tests, which include structural test, acoustic test, vibration test, and for example, wind tunnel test. Another thing to understand, simulating, we built models of the rockets and subject to wind tunnel test. For that, huge facilities and infrastructures are built in this country. Then once you build the launcher subsystem, everything is taken to our Sriharikota, from where we are launching the launches. There everything is assembled, and we need to have huge infrastructure for launching, which includes the launch pad systems, including propellant servicing, then the control centers and data acquisition system, checkout system for checking the vehicle. Lot of infrastructure is required in the launch builds. And another thing is, when a launcher lifts off, it generates huge noise called acoustic noises. And then this has to be really controlled. For that, we are having the acoustic suppression system. This is one of the systems which is essentially required to ensure safety of the launch pad and launch vehicle systems. Now I am coming to the second portion of my talk on the rocket propulsion. I think the rocket propulsion is the one which gives the propulsion system is the one which gives the muscle power for the launch vehicle to lift off from the launch pad, pass through the dense atmosphere, and take the launcher to the required place and place the satellite in the required orbit. And the propulsion system, easy to explain. You all would have seen the balloon filled with air. And if the air is released, what will happen when the air goes out? The balloon moves. Basically, the propulsion system works on Newton's third law of motion. In the propulsion system also, what we do is we ban. In the air, it is with low pressure, and when it moves, the balloon moves out. But in the launcher, we have to lift some 6,640 tons of vehicle, and we ban propellant inside a chamber. And that hot gases, high temperature hot gases, high temperature and high pressure gases are expanded. And when these things are expanded and expelled out, the launcher moves up. As per Newton's third law of motion, for every action, there is a reaction. The action is nothing but the hot gases escaping out of the motor cases. And when it moves out of the motor cases, the reaction is the one which causes the launcher to move. And I am not going through the fundamental equations and other things. And it is very simple to understand the propulsion system. Now coming to a launch vehicle, in a launch vehicle, almost 98% mass is the propulsion system mass, which includes 86% propellant mass and remaining associated propulsion system structural mass. And remaining is the other systems like equipment bay, payload, the rather satellite, everything is remaining something around 1.8 to 2%. I think you can understand easily the entire ability or the capability of the launch vehicle is depending upon the capability of the propulsion system. For example, if you take a GSLV Mark III vehicle, which is 640 ton lift-off mass, and the propulsion system mass is 98.3% of that. And these are all energy intensive devices and operating for short duration and releases the energy in a fast rate. Then coming to the satellite, also each satellite has got its own inbuilt propulsion system and meant for multiple purpose, that I will come back to that. In a satellite, almost 60% is the mass of the propulsion system. I used to explain to the colleagues, those who are not in the engineering field, with a simple example. You know, the difference between in the propulsion system, basically it consists of engine and the system meant for storing the propellant. Now, the purpose of the rocket engine is rocket engine and car engine. The purpose is almost similar purpose. You know, the car engine, what is the purpose? The car engine is operated to move either human beings or the materials from one place to another place. Same thing only, the rocket engine is operated to take the launcher from Earth to space to move, take either human being or satellites. That is the purpose. But the difference is, couple of differences are there. You take a car, it can go with a velocity of speed of something around 100 km per hour to 120 km per hour in Indian road condition. And for a rocket engine, rocket to place the satellite in the required orbit, as I told, we have to impart something around 20,000 km per hour to 37,000 km per hour is the type of velocity we have to impart. So that is the job the propulsion system is doing. Now you all will understand, I think you are all, some of your physics teachers, the propellant consumption, there are the fuel in a petrol car. You take a Maruti car, it uses petrol. Maruti car uses petrol and air as the fuel, and the petrol to air ratio is 1:3. And you can use do simple calculation, and one can conclude we consume 3.5 to 4 gram per second of air and petrol in the Maruti car, 3.5 to 4 gram per second. Against that, when our Mark 3 vehicle lifts off, we consume 4,400 tons per second of fuel. You can understand the difference, you know. A car is using hardly 4 gram per second of air and petrol, and a rocket, our Mark 3 rocket, when it lifts off, almost 4,400, 10 power 6 times of the fuel consumption. And now, if you see the power, it's a huge power actually. Car power is 88 horsepower, and a typical space shuttle main engine power is 37 million horsepower. And we used to say our typical rocket engines, 15,000 times of locomotive power is the power it gives. And another thing I used to say, it is a energy intensive device. One example I can give you, in the aircraft engine, to generate a thrust of 20 tons of thrust, we consume something around 1,000 kg per second of fuel plus air. Against that, we have developed a rocket engine called CE-20 cryogenic engine. To generate same 20 tons of thrust, only 40 kg per second fuel we are using. That means you can understand the energy, how it is effectively utilized in the system to generate similar thrust levels. And the launch vehicle propulsion, there are different types of propulsion system. We call it as solid propulsion, liquid propulsion, and hybrid. And basically, it is depending upon the state of the propellant. This classification is done. In the solid motor, the propellant will be in the solid form and get banned. It is banned and then it is expanded. And in the liquid engine, the propellants are in the liquid form. And in the hybrid motor, the oxidizer and fuel, there is basically oxidizer and fuel is required. One will be in the liquid form, another will be in the solid form. And liquid, again, depending upon the type of propellants, it is classified further into monopropellant, bipropellant system. We'll come back a little later. And depending upon the temperature, we call it a storable propellant. That is the temperature that the propellant will be under ambient conditions. It will be in the liquid form. And cryogenic propellant and semi-cryogenic propellant. Cryogenic propellant are the one, especially we use liquid hydrogen and liquid oxygen. Extreme low temperature propellant we use. You all may be knowing the hydrogen gas can be liquefied when the temperature is reduced to minus 253 degrees centigrade. So we reduce the hydrogen gas temperature to that and liquefy hydrogen in the liquid form. And oxygen we separate from air, and at minus 183 degrees centigrade, oxygen will be in the liquid form. And these two combinations we use in the cryogenic rocket engine. And semi-cryogenic we use, for example, liquid oxygen and kerosene. Kerosene is not our ordinary stove kerosene. It is the rocket grade kerosene, which is a totally purified thing. That is what is used. And the selection of this propulsion system is depending upon different criteria, depending upon the thrust requirement and so many things. Now, in the propulsion system, generally we use one terminology. In when we talk about fuels, or the wood or the petrol and other things, when you this one terminology you all know, calorific value of that fuels. Similarly, when it comes to propulsion system, we use one performance parameter called specific impulse, nothing but the thrust generated per unit weight flow rate of propellant. Whatever thrust in terms of kg generated per unit weight flow rate is the performance. We call it a specific impulse, and the numbers are given here. I think the cryogenic, these are all the chemical propulsion system numbers, and the solid is having moderate, air storable is little better than solid, and semi-cryogenic is having little better, cryogenic is the best. And of course, we have got LOX methane, and the selection of the propulsion system is depending upon lot of criteria. And coming to the solid motor, basically in the solid motor, we mix the oxidizer, I think ammonia. There are different types of oxidizer and fuels, and typical case oxidizer is ammonium perchlorate, and metallic fuel is aluminum, and with a binder, polymeric binder, the details are given here, and these are all mixed in the slurry form. Finally, it is casted in the motor case and cured, and finally it will be like a rubber product, like a solid form, and which is used in the rocket engine. Basically, it has got a grain. Grain is nothing but the total propellant, which is in the slurry form, later on cured. Then we are having a motor case. It can be metallic motor case or a composite motor. And then, when the propellant is burned, it will generate high temperature. So to protect the hardware, metallic or the composite hardware, in between there is a insulator, maybe which protect the motor case. Then basically there is a motor case, then there is a insulator, then we are having liner, then beyond that we are having the entire grind. That is the main portion of the solid motor. And there are igniter. There is a igniter which initiates through the electrical. Igniter itself is a big complex system, and it initiates the ignition, and the hot gases, high pressure, high temperature hot gases are generated by burning the propellant in a very controlled way, and which is expanded through the nozzle system, which generates the thrust. And then very simple to say this, but it's a very, very complex product. Product. In fact, in the initial phase of development, we have faced a lot of failures. In the early 1970s, whatever small motor it is generated, it used to simply blast, and then the entire team has wetted the hand, and today we have become master in developing these motors. And to our credit, we have built a lot of motors, and one of the smallest motor, what was used to us for impacting our Indian flag, the moon impact probe on moon surface using the Chandrayaan-1 through a small solid motor, which had only less than a kg propellant mass. And this gives the different solid motors built for our program. The heaviest solid motor is built for the LUM-3 vehicle. We are having two motors, each are having 207 tons of propellant, 207 tons of propellant, and both bands simultaneously with a band rate of, propellant band rate of 2100 kg per second. That means almost 4200 to 4300 kg per second is the propellant which is burning and getting exhausted for lifting this one. So this gives the different varieties of motor cases. Today, it is even though we struggled in the initial phase, today it is a child play for us. And coming to the next class of propulsion system called liquid propellant system, the solid motor, there is advantage. It generates a lot of thrust and very high thrust. Thrust to mass ratio is very high, and it is very simple. No dynamic elements. Once it burns, and it takes off the rocket. And but only thing is, you cannot once it burns, you cannot stop in between, and it will completely burn. That means if you are to inject the satellite precisely in the required orbit, when you achieve the required condition, you have to stop the motor, which is not possible in the solid system. Whereas liquid is not like that. You can stop in the appropriate place, and same hardware you can test in the ground and you can fly, and multiple times you can operate. So there are a lot of advantages, but then it is a complex system. The entire development in the world started in 1921. Till today, throughout the world, something around 1,300 types of engines are realized and put through the usage. And it is very easy to understand. Basically, the propellant is stored in the tank, both oxidizer and fuel. It is stored in the tank, and which is brought into a combustion chamber with the required pressure levels. And in the combustion chamber, this is banned and expanded through the nozzle system. And there are two types of system. One is called pressure fed mode system, in which the propellant is stored in high pressure tanks, and tank pressure is maintained to the required level through other systems. It is a very simple schematic. And from that, when the valves are opened and the propellant is fed into the combustion chamber, inside combustion is initiated, and combustion rather takes place in some cases, and gas is expanded, high pressure, high temperature gas is expanded through the nozzle system. And another system is wherever you need high thrust, we cannot keep the tank because if the huge pressure levels are required, then we use pumps, centrifugal pumps for pumping the propellant from the tank into the combustion chamber. And these pumps are driven by gas turbine, driven by gases generated by bleeding some quantity of propellant from the pump outlet. And then through the turbine, the pumps are driven, and the pumps are pumping the required flow rate to the required level. Now, I can give you one example. You know, our water pumps, what is pumping? It's all having the some 3 horsepower, 5 horsepower, this type of power, the household water pumps. And we are developing a pump, turbo pump system, which has 36 megawatt power, and the pump has to handle something around 645 kg per second of fuel flow rate with 600 bar pressure it has to generate. We are developing a semi-cryo engine which operates with a turbo pump system. The pumps have to really generate very high pressure and handle very high flow rates, and it is a very, very complex development game. And there are so many liquid rocket engines we have developed, and the thrust varying from 1 Newton to current operational engine, 800 kilonewton is the thrust of the engine. So many engines we have developed, and these are all the air-storable engines what we have developed. That means air-storable engine means the fuel is in the air-storable liquid form. Basically, we are using nitrogen tetroxide and unsymmetric dimethyl hydrazine. And some places we use monomethyl hydrazine and mixed MON3, mixed oxides of nitrogen. MON3 is used, and there are different types of fuels. And these are all the typical air-storable engines developed by ISRO. And one is the engine, another one is the stage. Stage has got the propellant tanks and associated system to store the propellant. This is one of the stage, the heaviest stage, and developed for the Mark III vehicle. We call it as L110 stage. Basically, it has got 110 tons of propellant, N2O4 and UH25 propellant, stored in 4-meter diameter tank, and the length of the stage is something around 16 meter, powered by 2 engines, each generate 800 kilonewton thrust. And next is the cryogenic stages. You know, in the cryogenic stage, as I told, we use liquid oxygen and liquid hydrogen. Liquid hydrogen temperature is minus 253 degrees centigrade, and liquid oxygen minus something around 78 Kelvin to 80 Kelvin is the type of temperature. And among chemical propulsion, the cryogenic propulsion gives the best performance. Almost, I will say, 1.7 times of solid propulsion. So these are essentially required for the launch vehicle program as upper stages for placing the satellites in the GTO and other required orbits. And in fact, this is one of the technology we have developed in the world. Only 5 countries are having this technology. And the problem is such a low temperature, even producing and storing everything is very complex. And hydrogen, you know, if you handle properly, it will work as a fuel. If you don't handle properly, it will explode. And then one has to be extremely careful in the entire handling, production, everything one has to be handled. And in fact, we have developed two cryogenic stages, one for Mark-3. I think the Mark-3 vehicle, the upper stage, there are two solid motors, and central core is the L110 stage, and upper stage is the cryogenic stage. And the Mark-3 vehicle, to place the satellite in the orbit, something around 37,000 km per hour velocity vehicle has to give. Out of that, 50% velocity is given by the upper stage. Because by that time when the upper stage comes into action, all the lower stages are separated out and the mass is less, and it gives almost 50% velocity. And this we have totally indigenously developed, and India is one among 6 countries having this complex technology in our hand. And I think when you have seen the photograph of the engine, it looks simple, but it is not simple. It is a very complex system. It has got, I think some of the systems I have given, it has got, for example, in the hydrogen oxygen engine working with the hydrogen oxygen propellant, there is a hydrogen pump, there is an oxygen pump, there are turbines, there are so many control components, and there are so many systems associated with that. Same way when you talk about a stage, we need to have propellant tanks, structures, associated control components. So many things are required. And next propulsion system is the semi-cryogenic propulsion system, where we use liquid oxygen and rocket grade kerosene for the propelling the stage or propelling the rocket. And currently we are, the advantage of this is compared to this cryo, here the performance is a little inferior, but then the density of hydrogen is much lower. So to store the hydrogen, we need huge tank, and density of kerosene is much higher, almost 10 times higher. Thereby the tank and storage system mass will come down. So that has got some advantage. And we are developing currently a 200-ton thrust engine, and which works on rocket grade kerosene and liquid oxygen. And we have built a facility, almost 1,000 crore worth of facility, and that small photograph is a facility worth 1,000 crore. Recently, we have successfully tested a couple of systems, and in another 2 years, we are going to deploy this system for the rocket, for our rocket. And currently, our LVM-3 maximum payload, what we can lift is something around 4,200 kg in geotransfer orbit, or something around 9,000 kg to low Earth orbit. And to enhance the payload almost 25% with the same cost, we are going to deploy the semi-cryo system with a uprated cryogenic upper stage. We will be achieving this. Maybe you all will hear the news in another 2 years time frame from now on the induction of semi-cryo stage for the Mark-3 vehicle. And another important system is the propulsion system, where we use liquid oxygen and methane. You know, methane is available in other planets also, and this has got a lot of advantage. And we have realized a technology demonstrator, and already we have tested a couple of tests, and we have understood the technology. Right now, we are developing a engine. Already the project is approved using liquid oxygen and methane, which has got moderate performance and repeatable use. It can be used. And another thing is, future, if you go to other planets we can liquefy methane and we can come back. So that is another thing which is in the mind, and we are developing this engine. Now coming to our launch vehicle, as I told, currently we are having 6 vehicles in operation, and the heaviest vehicle is our Mark-3 vehicle, capable of placing 9,000 kg in the low Earth orbit. Now we are developing a new rocket called new generation launch vehicle. We have named it as Surya as the vehicle, and which is capable of taking 32 tons to low Earth orbit. Again, it is almost 4 times of the present Mark-3 vehicle capability, approximately 4 times. And there is a core vehicle and with 2 strap-ons. And with the core vehicle, it is a 3-stage vehicle, and first stage and second stages uses multiple LOX methane engines, and upper stage is a cryogenic engine. This vehicle is currently under development, and we are also thinking of further developing heavy lift launches. That's all thinking process is on. And coming to another propulsion system called air breathing propulsion. You know, when a rocket lifts off, we store both oxidizer, liquid oxidizer and fuel, and we are lifting up. Imagine the oxidizer mass is almost 70% of the fuel mass. Imagine we don't take oxidizer, and instead on the way up to the atmospheric region, you use atmospheric air, then the lift-off mass of the rocket will be less. So one propulsion system, we call it as air breathing propulsion system, in which we take only fuel, but this cannot work in the deep space environment because no air there. In the atmospheric region, it can work. So we admit air in the appropriate condition with high velocity, high Mach number of 5, 6, that order, and we inject either kerosene or hydrogen and use for the propulsion. This is called air breathing propulsion. In fact, you all will appreciate one thing. In any important function, when somebody has to light a lamp, how much they will struggle. And when you light a lamp, imagine the fan is on. People cannot light the lamp. That is the situation. And here, the air will enter with a velocity equivalent to Mach number 5 to 6. It is like a hurricane, it will enter, and there we have to initiate the ignition and sustain. And India is one of the countries which has successfully demonstrated the technology in the first attempt on 28th August 2016. And in another couple of months, that time only we ignited and sustained the ignition. We demonstrated in a couple of months, we are going to demonstrate this technology for 250 seconds. Continuously, you will hear the news very shortly, maybe in 2 to 3 months' time. The development work is going on in the advanced level. Another thing, as I told, hybrid. In the solid rocket, we both oxidizer and fuel is mixed and kept in the motor, and in the liquid, both oxidizer and fuel is kept separately. And advantages, you can stop in between. And to draw both advantages and drawbacks of both together, there is a system called hybrid. One thing, either the fuel will be in the solid form and the oxidizer will be in the liquid form. So you can admit oxidizer whenever required and ban. And this is another system people have developed. We have also done some experiments. And coming to the spacecraft, the launcher placed the spacecraft generally for the communication spacecrafts are placed in the elliptical orbit in the Earth. From there, we have to take it to the required place. And also, we have to stabilize and maintain in the orbit, because when the satellite is rotating in the orbit, there will be a lot of disturbances and the satellite orientation has to be maintained. For different purposes, we need spacecraft propulsion systems. And each satellite, whatever is going, will have propulsion system for varying purpose. The purpose is given: orbit rising, orbit maneuver, station acquisition, deorbiting, and inclination correction, and so many purpose it is required. And as I told, typically in a chemical propulsion driven satellite, out of the total mass of the satellite, 60% mass is the propulsion system mass. And this is a typical different type of propulsion system. It can be chemical propulsion, electrical propulsion, and other different propulsion systems. And chemical propulsion, it is identical to the rocket engines. We have either single propellant, which is decomposed and generate thrust, or the bipropellant system. There will be oxidizer and fuel stored in independent tanks that can be used for burning in the combustion chamber in a controlled way and generating the thrust. And now, if you take the Chandrayaan-1, you all know, generally the students used to ask, India, we got independence 47 years back, and in 1947, 76 years back, and with respect to space program, where we stand. In fact, a couple of places we have become number one. One is Chandrayaan-1 is the first interplanetary mission, and we send the spacecraft Chandrayaan-1 to the moon's orbit. It was not a landing mission, moon's orbit. And Chandrayaan-1, which found water molecule for the first time on moon surface and made all Indians proud. And India is the first country, of course, along with USA together, we found water molecule on the moon surface, and every Indians it made proud. Now, this satellite was launched by our PSLV vehicle, and it placed in the orbit of something around 22,000 kilometers. From there, almost 4 lakh kilometers we had to travel. And that job was done by the propulsion system. I think you are seeing the engines, liquid approach motor, along with the control thrusters. And it was operated a couple of times, and it went to moon, and finally it was captured and made all Indians proud. And as I told, there was one moon impact probe, which is on the right corner, through which we placed our tricolor on the moon surface. There, a small solid motor was used. And then Chandrayaan-3, you all know, this is a proud baby of the entire country. and we successfully landed near the South Pole. And there we used Mark 3 vehicle, LVM-3 vehicle, which took 3,900 kg prestigious Chandrayaan-3 system from ground to a 36,000 kilometer orbit. It placed in that orbit. From there, the Chandrayaan-3, which is 3,900 kg satellite, but 3,013 kg is the propellant and propulsion system. From there, through a propulsion module, which had a propulsion system, it was operated multiple times, almost 43 days, and it was taken to moon surface, and then it was captured in the moon surface. And after that, on 23rd August, it was rotating in the moon surface with something around 6,700 kilometers per hour. So in the Chandrayaan-3, there were two systems, basically three systems. One is the orbiter, the propulsion module, which took it to moon. Another one is a lander module through which the entire landing operation was done, which had four throttleable engines, 4 engines of 800 Newton. On the left side, you are seeing 4 engines were there. This was used a body which was rotating around 6,700 kilometers per hour, which is 8 times of the aircraft speed. In 19 minutes, the speed has to be reduced. Rather, the motor has to work to reduce the velocity and brought the Chandrayaan-3 to rest and soft landing. So this job was also done. That means the propulsion community, rather the propulsion system, played a crucial role. Number one, taking Chandrayaan-3 from the ground to the 36,000 kilometer orbit. From there, taking to 4 lakh kilometer and capturing there, which is done by propulsion system, and making soft landing, which was also done by the propulsion system. Of course, there are so many satellite systems responsible for successful landing, which include navigation, guide and control, camera systems, and inertial. So many systems are there, and propulsion system does that entire crucial role. You would have seen the engines, how it was firing the opposite direction and reducing the velocity. And you know, the Indians, I think in the mathematics teacher, you all know, Indians were made proud by the discovery of zero those days. And on 23rd August, we made 3 parameters: the horizontal velocity, vertical velocity, and the altitude equivalent to near zero, and made all Indians proud through this mission. And another one important thing is the Aditya L1. Aditya L1, India is the 4th country which has built a satellite called Aditya L1, 1,480 kg satellite with 7 important payloads for studying the sun. And here again, the PSLV vehicle was used for placing the satellite in the low Earth orbit, rather elliptical orbit. From there, some 22,000 kilometers it was placed. From there, it has to be taken to not 22, something around 20,000, 19,520 kilometers precisely. 240 kilometers by 19,520 kilometer elliptical orbit, it placed the satellite. From there, almost 15 lakh kilometers, the satellite has to be taken, and we have to capture in the L1 place, which is a stable orbit, which is almost 1% distance between Earth to Sun. There it has to be placed. This was done by the propulsion system in the satellite. And really, whenever we operate, it is all crucial movements to operate. It should not escape and go in some place. And another important thing, you know, the Mars orbiter mission, India is the only country and first country which successfully sent and successfully accomplished a mission to Mars and successfully captured almost, you know, the distance what has to be traveled is 68 crore kilometer is the distance you have to travel, and this was accomplished by the propulsion system. You please imagine, as mathematics and physics teachers, if there is when you travel 68 crore kilometer, 0.1 degree error is there, where it will go? It will not go to the required orbit, it will go and escape somewhere. And the Indian Space Research Organization done perfect job and made properly travel in the right orbit, right path, and captured in the required place. And after capturing, you have to reduce the speed and stabilize there. And so our engines were operated almost after 295 days successfully. You imagine a scooter or car in the house. You don't operate for 295 days and operate almost after 1 year. You know what will happen, whether it will work or not. Lot of things has to be done, then only it will work. But here, these engines are not like that. It perfectly operated after 295 days. and we could capture in the Mars orbit and made all Indians proud. And another system is called electric propulsion system for satellites. And electric propulsion system, basically what we use is using electrical energy. From the solar energy, electricity is produced, and from the electrical energy, we make plasma of the required propellant. We generally use xenon as the propellant, and which is made as plasma form and accelerated generating thrust. And the performance in terms of specific impulse is almost 5 to 6 times of the chemical propulsion. Minimum 3 times advantage is there, but the thrust it will generate is less, because for generating thrust you need huge electrical energy. And but advantage is it is having high specific impulse, high performance. For example, as I told, take Chandrayaan 3. Chandrayaan 3, out of 3,900 kg satellite mass, something around 2,800 kg propellant, which was used for traveling purpose. Now, if you use electric propulsion, then the propellant mass will drastically come down, and you can use useful payload out of it. And this is one of the system currently under development. And before this year end, we are going to launch this. A 300 millinewton electrical thruster is getting developed in LPSC in Trivandrum, and we are going to launch. And another advantage, you take a typical communication satellite of 5.5 ton class communication satellite, the useful payload is only 900 kg, and other things are all other system, mainly propulsion system. If you use electric propulsion system, instead of 5.5 ton, same useful payload can be placed by 3.5 ton class satellite. That is the advantage. So it is, we are on the job. Another thing is nuclear propulsion, where the hydrogen, hydrogen is a low molecular weight, high energy fuel. Hydrogen in the cryogenic engine, what we use is hydrogen and oxygen we band together, and which is expanded. And in the nuclear propulsion, the hydrogen gas is heated, hydrogen liquid is heated by the isotope, rather the nuclear power plant, and that hot gas is expanded, generating thrust. And if you see the performance of any propulsion system, I told ISP, the performance is proportionate to root T by M. T is the temperature of propellant, not in the storage condition, in the expanding condition, and root T by M. M is the mean molecular weight, and hydrogen being the low molecular weight, it generates higher performance. And this type of systems are also currently under development by various spacefaring nations, but never flown. And this is one of the new development, one can really work on this. And RF-based propulsion system, where we use RF power for generating the propulsion. And another thing, you all would have heard the human spaceflight program, and in which we are going to take 2 or 3 of our own brothers or sisters to space and bringing them back safely. For that, we are developing a lot of systems. And one thing is the launch vehicle Mark 3 is identified, but it is not the same launch vehicle Mark 3 systems. The solid propulsion, the core liquid, and the cryogenic propulsion system, everything has to be human rated. That means we have to build additional redundancies and margins in order to improve the reliability. That is one. And the vehicle takes to a altitude of something around 170 kilometers. From there, we are having an orbital module. There is a service module and a crew module. These two are having two independent propulsion systems. The orbital module, the service module, takes from 170 kilometers to 400 kilometers. And there it keeps them to the required number of orbit or required number of days safely. So for that purpose, there is a propulsion system, and currently it is in the advanced stage of development. And some of you can come to LPSC Valiamala and IPRC near Kanyakumari to see those systems. That is one of the systems we are developing. Another thing is, after keeping them for the required time frame, later on to bring them back, the human being will be in the crew module, and there is a propulsion system, basically an engine system with multiple thrusters, which is operated to bring them from the 400 kilometers to back to something around 170 to that type of distance to bring them back safely. For that, the crew module system is employed from 400 kilometers to the required place. Using this system, they are brought back safely. And these systems are also getting developed. Another thing is, in case when after the crew go into the system, in case of any anomaly in the launcher at different phases, they have to be taken to safely. So we are developing a crew escape system, basically a solid motor system, which can be used during the launcher operation up to the solid motor and L1 ton operation. And in case of any anomaly, this fast burning, high efficient motors are operated and the crew is taken safely to faraway place. Then from there, they will land safely by utilizing parachutes. And to demonstrate this crew escape system, very recently we had built a test vehicle, and that test vehicle, using the test vehicle, a crew escape system was successfully demonstrated. Basically, a rocket was built using the liquid-based engine, and that rocket took off successfully. On the top, we had the orbital module, and orbital module was separated, and then using the crew escape system, it was brought back safely to the designated site. And in fact, we went and received, it was later on captured by our Navy ship, and we went and received the module. And like this, lot of experiments has to be done before going for the Gaganyaan program. And to make the Gaganyaan program successful, lot of systems are required, but the propulsion system is one of the key, which is, as I told, there are solid motors which are required for the launcher and for crew escape system, and liquid and cryogenic engines are required for the launcher. Then propulsion system required for taking them to the required place of 400 kilometers and keeping them safely, and propulsion system required for bringing them back from 400 kilometers to the safe place. So propulsion system plays a crucial role. And in fact, as I told, the launcher capability is purely dictated by the capability of the propulsion system. So propulsion system plays a very, very key role. Now coming to the ISRO's future targets, I think you all may be knowing our Honorable Prime Minister has already rolled the plan. And 2023, we had successfully accomplished the Chandrayaan 3 mission. 2024, January 6, we placed the Aditya L1 in the required orbit. The L1 place, it was commissioned. And 2024, we have declared as Gaganyaan testing phase, and we are going to have first Gaganyaan unmanned mission. And 2025 last quarter or 2026 beginning, we are planning to have further missions, including the human to be sent to space and bring them back safely. And 2026, we are going to have further continuation of Chandrayaan 3, Chandrayaan 4 mission, and which will bring, Chandrayaan 1 water molecule. Chandrayaan 2, we had a soft landing, but unfortunately soft landing was not successful. But then the orbiter is revolving around the moon, going to work for 7 years, and it is sending wealth of data, and it is having an on-orbit high resolution camera, which is the best in the orbit. We are having the camera, and it is the best camera ever built and working in the orbit. And Chandrayaan 3 brought glory to Indians by successfully soft landing. Now, Mars orbiter mission, you all know. And another important thing probably I want to highlight is the PSLV vehicle. Now we are celebrating 60 years Indian space program from the first rocket launch. Almost 60 years we have completed. 60 rockets we have lifted off PSLV. Out of 60, 58 successful missions. And that PSLV has done one important thing. When we celebrated 75 years of independence, it hoisted our national flag in the space through that mission. One of the mission it was done. And now Chandrayaan 4, we are targeting 2026, which will be taking sample from moon and bring back the sample to India for doing studies. And we are going to build a space station. 2035, we'll be having our own space station. Towards the is going on, and for that also a lot of systems are required, including propulsion system development. And 2040, India is set to send 2025, we are going to send our human being to low Earth orbit and bring them back safely. And 2040, Indian will be landing on moon, and we are going to bring them back safely. So these are all the programs which are in the pipeline. And this gives the total roadmap of on the propulsion system. I think Indian space program I am not totally addressing. And this gives probably today where we stand and how we are going to move forward, and we have to develop lot of propulsion systems and the launches. Right now the Mark III is already developed and qualified, and we are going to index semi-cryo, and we are going to have Gaganyaan program. Then we are it will fly. Then we are going to build a air breathing rocket engine based system. Then we are going to build a new propulsion system, including right now we are developing a large methane engine that approval has come, and approval means for pre-project approval we have got, and new propulsion systems we are going to develop, and a high thrust liquid engine maybe 250 to 300 ton. This is in the thinking process. That also may be required for meeting the ISRO's program. And in nutshell, I want to tell Indian space program, as you are aware, 1947 we got independence. 1962 the program started. When we started the program, as I told in my initial slide, we are 60 years behind the advanced countries, and today we are doing great job. In fact, application I have not talked. Somebody else would have talked. So much applications, including Earth observation, communication, navigation, and scientific mission. So many applications are there, and today we are one among 6 strong spacefaring nations. I want to tell that before we celebrate independence, 100 years of independence, we will be matching in. When we started space program, we were 60 years behind advanced countries. But now we have bridged the gap, and couple of places we have become #1. And when we celebrate 100 years of independence, India will be really a very high level in terms of space program, and we are going to contribute for making this country as a developed country. On this occasion, I would like to thank all the teachers. Actually, teaching profession is a noble profession. Let me salute all teachers. In fact, I used to say to my teachers, we have never seen God directly, but we have seen the God through the face of teachers. That's what I used to always tell to my teachers. So you are doing a great job, and hope I have done little justice in delivering this talk on the launch vehicle and propulsion system. Very difficult to give the talk in 60 minutes to 65 minutes time frame, a work which is done over 60 years of time frame. And with that, I request you to inculcate a great culture among student community. You have to really bring out excellent student, not academically. Both moral value has to be pumped in the minds of the students, and you have to really contribute through the student community for making this country as a developed country before we celebrate 100 years of independence.